Nuclear weapons are often talked about as if they are all the same, but in reality, there are many different types. Over the past century, scientists have developed several designs based on different nuclear reactions and engineering approaches. Some weapons rely purely on splitting atoms apart. Others combine multiple nuclear reactions into one device to produce explosions thousands of times more powerful than the bombs used in World War II. To understand how these weapons evolved, it helps to look at them step by step, from the simplest and least powerful designs to the far more complex weapons that came later. Level 0. Radiological weapon, dirty bomb. The lowest level in terms of nuclear destructive power is something often called a dirty bomb. Technically, a dirty bomb is not a nuclear explosion at all. Instead, it is a conventional explosive combined with radioactive material. When the explosive detonates, it spreads radioactive particles into the surrounding environment. The goal of this type of weapon is not massive destruction, but contamination and panic. Buildings, streets, and infrastructure can become contaminated with radioactive dust, forcing large areas to be evacuated while cleanup takes place. Unlike nuclear weapons, dirty bombs do not create a nuclear chain reaction. They rely on normal explosives, such as TNT or similar materials, to disperse the radioactive substance. The immediate blast damage is similar to any conventional bomb of the same size, but the long-term effects come from radiation exposure. People in the contaminated area could be exposed to radioactive particles that increase the risk of cancer or other health problems over time. Because radioactive materials used in medicine, research, or industry can sometimes be stolen or misused, dirty bombs are often discussed in the context of terrorism. However, their destructive power is far lower than that of true nuclear weapons. They represent the lowest level in terms of nuclear-related weapons. Level 1. Gun-type fission bomb. The first true nuclear weapon ever used in war belonged to the category known as the gun-type fission bomb. This design relies on nuclear fission, a process where heavy atomic nuclei split apart and release energy. The bomb dropped on Hiroshima in 1945, known as Little Boy, used this exact type of mechanism. Inside the weapon are two separate pieces of highly enriched uranium-235. Each piece is too small to create a nuclear explosion on its own. In nuclear physics terms, they are subcritical masses. The weapon works by firing one piece of uranium into the other using conventional explosives, similar to how a bullet is fired through a gun barrel. When the two pieces collide, they form a single supercritical mass. Once this happens, neutrons begin striking uranium atoms and splitting them apart. Each fission event releases more neutrons, which then split additional atoms. This rapidly creates a runaway chain reaction. Within a fraction of a second, billions of atoms split apart, releasing enormous energy in the form of heat, radiation, and a powerful blast wave. The Hiroshima bomb produced an explosion equivalent to about 15 kilotons of TNT. Compared to later nuclear weapons, this is relatively small, but it was still powerful enough to devastate a large portion of the city. Gun-type bombs are relatively simple compared to other nuclear designs, but they require large amounts of highly enriched uranium, which is extremely difficult to produce. Because of this limitation, scientists soon began developing more efficient nuclear bomb designs.
Level 2. Implosion-type fission bomb.
The next major development in nuclear weapon design was the implosion-type fission bomb. Instead of firing two pieces of nuclear fuel together, this design compresses nuclear material inward from all sides. The core usually contains plutonium-239, another material capable of sustaining a nuclear chain reaction. Plutonium behaves differently from uranium and cannot be used effectively in the gun-type design. The reason is that plutonium has a higher rate of spontaneous neutron emission. If scientists attempted to use plutonium in a gun-type weapon, the chain reaction would likely begin too early, before the material fully assembled. This would produce only a small explosion, known as a fizzle. To solve this problem, engineers developed the implosion design. In this type of bomb, a sphere of plutonium sits at the center of the device. Surrounding it are carefully shaped conventional explosives, known as explosive lenses. These lenses are arranged so that when they detonate, the shock waves move inward evenly from all directions. The explosions compress the plutonium core, squeezing it into a smaller and denser shape. As the density increases, the plutonium becomes supercritical, and a chain reaction begins. Because the material is compressed before the reaction starts, the explosion becomes much more efficient. A larger percentage of the nuclear fuel undergoes fission before the bomb destroys itself. The bomb dropped on Nagasaki in 1945, known as Fat Man, used this implosion design. It produced an explosion equivalent to about 20 kilotons of TNT. The implosion method became the foundation for many later nuclear weapons because it allowed smaller, more efficient warheads to be built. Scientists soon realized that even greater explosive power could be achieved by combining fission with another type of nuclear reaction. Level 3. Boosted fission bomb. As nuclear weapons continued to evolve after World War II, scientists looked for ways to make fission bombs more powerful without making them significantly larger. One solution was a design known as the boosted fission bomb. At first glance, a boosted fission bomb looks very similar to the implosion-type weapon described earlier. It still contains a core of fissile material, such as plutonium-239, surrounded by conventional explosives that compress the core inward. However, inside the center of the plutonium core, engineers add a small amount of fusion fuel, usually a mixture of deuterium and tritium, which are heavy isotopes of hydrogen. When the bomb detonates, the implosion compresses the plutonium core and starts a normal fission chain reaction. The heat and pressure from that reaction become so extreme that the deuterium and tritium inside the core briefly undergo nuclear fusion. Fusion is the process where light atomic nuclei combine into heavier ones, releasing enormous amounts of energy. This fusion reaction produces a burst of high-energy neutrons. These additional neutrons dramatically increase the efficiency of the fission reaction happening in the surrounding plutonium. In simple terms, the fusion fuel acts like a catalyst that makes the fission process far more effective. More atoms split before the weapon blows itself apart, which increases the explosive yield without requiring much additional nuclear material. Boosted fission designs became extremely important because they allowed nuclear weapons to become smaller, lighter, and more reliable. Many modern nuclear warheads are believed to use some form of boosting because it improves performance while keeping the size compact enough to fit inside missile warheads. Even though boosting involves a small fusion reaction, the majority of the explosive energy in these weapons still comes from fission.
Level 4. Thermonuclear bomb, hydrogen bomb.
The most powerful nuclear weapons ever built belong to a category known as thermonuclear bombs, commonly called hydrogen bombs. These weapons rely mainly on nuclear fusion rather than fission. Fusion is the same process that powers the sun and other stars. In fusion reactions, light atoms, usually forms of hydrogen, combine under extreme pressure and temperature to form heavier atoms, such as helium. During this process, a tremendous amount of energy is released. However, fusion reactions require temperatures of tens of millions of degrees to begin. Scientists solve this problem by using a fission bomb as the trigger. In a thermonuclear weapon, the device is built in two stages. The first stage is a standard fission bomb that detonates and produces intense heat and radiation. This energy compresses and ignites a second stage containing fusion fuel, often lithium deuteride. As the fusion fuel is compressed and heated, fusion reactions begin. These reactions release huge numbers of high-energy neutrons, along with enormous amounts of energy. In many designs, those neutrons also cause additional fission reactions in surrounding materials, such as uranium. This combination of reactions creates an explosion far larger than any pure fission bomb could produce. Hydrogen bombs can reach explosive yields measured in megatons of TNT, which is millions of tons of explosive power. For comparison, The Hiroshima bomb had a yield of about 15 kilotons. Some thermonuclear weapons are more than 1,000 times more powerful than that. One of the most famous examples is the Tsar bomber, tested by the Soviet Union in 1961. With a yield of about 50 megatons, it remains the most powerful nuclear explosion ever created by humans. The blast was so powerful that windows shattered hundreds of kilometers away, and the mushroom cloud rose more than 60 kilometers into the atmosphere. Thermonuclear weapons became the dominant form of nuclear warhead during the Cold War because of their enormous power and scalability. Engineers can design them to produce yields ranging from a few hundred kilotons to many megatons. Level 5. Neutron bomb. While most nuclear weapons are designed to maximize blast and heat, one type was specifically designed to maximize radiation. This weapon is known as the neutron bomb, or more formally, an enhanced radiation weapon. A neutron bomb is a specialized type of thermonuclear weapon designed to release a large burst of neutron radiation while producing a relatively smaller blast. In a typical nuclear explosion, much of the energy goes into heat and shock waves that destroy buildings and infrastructure. In a neutron bomb, the design allows more high-energy neutrons from the fusion reaction to escape into the surrounding area. These neutrons can penetrate materials and living tissue very effectively. As a result, the weapon produces intense radiation capable of killing people within a certain radius, while causing comparatively less structural damage to buildings. The concept behind this weapon was primarily military. During the Cold War, some strategists believed neutron bombs could be used against armored formations, such as tanks. The neutron radiation could penetrate the armor and incapacitate crews inside, while leaving vehicles largely intact. Because of the ethical concerns surrounding such a weapon, neutron bombs became highly controversial. Some critics describe them as weapons designed specifically to kill people while sparing infrastructure. While a few neutron weapons were developed and deployed during the Cold War, their role in modern arsenals remains limited and politically sensitive. Despite their unique design, neutron bombs still rely on thermonuclear reactions, and therefore belong to the broader category of fusion-based nuclear weapons. In the next stage of nuclear weapon development, scientists experimented with devices designed to produce even more extreme effects.
Level 6. Salted nuclear bomb.
At this stage, nuclear weapons move beyond simple destruction and into designs intended to contaminate entire regions for long periods of time. One of the most infamous theoretical designs is known as a salted nuclear bomb. The concept was first proposed by physicist Leo Szilard during the early years of nuclear weapons research. A salted bomb is not a completely different type of nuclear reaction. Instead, it is a modified thermonuclear weapon designed to produce massive amounts of long-lasting radioactive fallout. The idea is relatively simple. Surround the nuclear weapon with materials that become extremely radioactive when exposed to the intense neutron radiation from the explosion. One commonly discussed example is cobalt. If a thermonuclear bomb were wrapped in cobalt metal, the neutron radiation from the blast could convert it into cobalt-60, a highly radioactive isotope. When the bomb detonates, this newly created radioactive material would be scattered across a wide area. The resulting fallout could contaminate land for years, possibly decades. Unlike normal nuclear weapons, where much of the radioactivity decays relatively quickly, cobalt-60 has a half-life of more than 5 years. That means the radiation would remain dangerous for a long time after the explosion. A salted bomb is sometimes described as a doomsday weapon because of its potential to contaminate enormous areas of the planet. However, there is no evidence that such weapons were ever actually deployed. Most scientists and military planners considered them strategically unnecessary and ethically extreme. Even by the standards of nuclear warfare, the idea of deliberately maximizing long-term radiation was widely viewed as crossing a dangerous line. Level 7. Multi-stage thermonuclear bomb. As nuclear weapons technology advanced during the Cold War, engineers began designing weapons with multiple stages to increase their power even further. A multi-stage thermonuclear bomb builds on the basic hydrogen bomb concept, but repeats the process several times inside a single device. In a typical two-stage thermonuclear weapon, a fission bomb triggers a fusion reaction in the second stage. In a multi-stage design, the energy from that second stage can be used to ignite yet another stage of fusion fuel. In theory, this process can continue with additional stages, allowing the explosive yield to grow dramatically. Each stage acts like a new layer of fuel that is ignited by the previous one. This design is one reason thermonuclear weapons can reach such enormous explosive powers. The Tsar bomber, tested by the Soviet Union, is believed to have been based on a multi-stage design. Originally, engineers planned for the bomb to produce about 100 megatons of explosive power. However, the test version was intentionally reduced to about 50 megatons to limit radioactive fallout and protect the aircraft delivering the bomb. Even at half its intended strength, it became the most powerful explosion ever created by humans. The blast wave circled the Earth multiple times, and the mushroom cloud rose into the upper atmosphere. Multi-stage thermonuclear weapons demonstrated that nuclear explosive power was not limited by simple engineering constraints. In principle, weapons could be built with almost unlimited yields, though practical military considerations eventually shifted focus towards smaller, more precise warheads instead of larger bombs.
Level 8. Tactical nuclear weapons.
Not all nuclear weapons are designed to destroy entire cities. Some are built for use on a much smaller battlefield scale. These are known as tactical nuclear weapons. Tactical nuclear weapons are generally lower in explosive yield than strategic nuclear weapons. While strategic weapons may produce explosions measured in hundreds of kilotons or megatons, tactical nuclear weapons may have yields ranging from fractions of a kiloton up to several tens of kilotons. The goal of these weapons is to target specific military objectives rather than large urban areas. They could theoretically be used against troop formations, military bases, airfields, or armored units. Because of their smaller yields, tactical nuclear weapons can sometimes be delivered using artillery shells, short-range missiles, or even specialized aircraft. During the Cold War, both NATO and the Soviet Union developed large numbers of tactical nuclear weapons as part of their military strategies. Some designs even allowed the explosive yield to be adjusted depending on the situation. Despite their smaller size, tactical nuclear weapons are still extremely destructive compared to conventional explosives. Even a weapon with a yield of a few kilotons could devastate a large area and cause significant radiation effects. For this reason, their potential use remains one of the most controversial topics in nuclear strategy today. Level 9. Strategic nuclear warheads. At the highest level are strategic nuclear weapons, the largest and most powerful warheads in modern arsenals. These weapons are designed primarily for use against major targets such as cities, industrial centers, or military infrastructure. Strategic warheads are typically mounted on intercontinental ballistic missiles, ICBMs, submarine-launched ballistic missiles, or long-range bombers. Many of these missiles carry multiple warheads using a system known as MIRV, which stands for Multiple Independently Targetable Re-entry Vehicles. A single missile can release several nuclear warheads, each capable of striking a different target. This technology dramatically increased the destructive potential of nuclear arsenals during the Cold War. Modern strategic warheads are usually thermonuclear weapons, with yields ranging from several hundred kilotons to over a megaton. Although these yields are smaller than the largest Cold War bombs, the ability to deliver many warheads accurately makes them extremely powerful weapons. Strategic nuclear forces are designed primarily as a deterrent,
meaning their main purpose is to prevent nuclear war by ensuring that any nuclear attack would trigger a devastating response. This concept, known as mutually assured destruction, shaped global nuclear strategy for decades. The existence of these weapons remains one of the defining realities of the modern world. They represent the most destructive technology humanity has ever developed, capable of reshaping entire regions of the planet in a matter of minutes.
Nuclear weapons evolved rapidly in just a few decades, moving from the relatively simple fission bombs of World War II to the extremely complex thermonuclear warheads that exist today. What began as a scientific discovery about how atoms release energy eventually became one of the most powerful technologies ever created by humans. Some nuclear weapons were designed to maximize blast and heat, others to increase radiation, and some even explored the idea of contaminating entire regions for years. But regardless of the design, all nuclear weapons rely on the same fundamental principle: releasing the enormous energy stored inside atomic nuclei. Today, thousands of nuclear warheads still exist around the world, and their destructive power remains unmatched by any other weapon. Understanding how these weapons work is not just about science or history. It also shows how powerful the forces inside the atom truly are, and why the responsibility of controlling them is one of the most important challenges humanity faces.